Okay, so now we're going to talk about doing matrix arithmetic with partitioned matrices. And so what we'll often want to do is consider a matrix as a collection of either rows or columns or even blocks, which I'll show you in a minute. I'll show you all of this in a minute, rather than individual elements. So oftentimes with rows, we're talking about observations. With columns, we'll be talking about variables. And we just want to specify a matrix by specifying what the rows are or what the columns are. And so when we write something that looks like this, A equals A1, A2, AN, notice these things are all bold and they have vertical lines. When we write this, what we're going to do is we're going to view the matrix as a collection of column vectors. So each column vector, AI, will most often be a variable. When we're doing text mining, it may be a document. And so this A1 here represents this entire column. Now, we already have some notation for this with the star. This would be A star 1. But that gets a little bit clumsy and rough on the eyes. So what we're going to do is just write it like this, and we're going to drop those stars out. And it'll always be clear whether we're talking about rows or columns because we're going to write them either vertically or horizontally. So, like I was saying, with the row vectors, we'd specify it in this way. Here was written on the left. And each of these AIs represent a row vector. And so when we write this, we're going to understand that this is a matrix, it's not a vector. And what we're interested in is the rows. We can also draw divisions in the matrix to partition it into blocks. So here I have a 4x4 matrix, and I'm going to block it off into these little 2x2 blocks. And each of these 2x2 blocks is going to have a name. So here, B is this top left corner. That's this 2x2 block in blue. And so why might I want to do this? Well, I don't want to get too far ahead of us, but if this might be well, we talked about networks, right? So this might be an adjacency matrix. So if this is an adjacency matrix, there might be two individuals here that are very closely linked. So I'm interested in the links only between this one group of individuals. Here there'd be only two, but in practice, this block may be much bigger. So we might have some subgroup of individuals that I want to focus on. So this block notation gets pretty nice because one of the things we can do is we can actually multiply block partition matrices as if those blocks are entries in a new matrix. So here I have that same matrix that I had on the previous slide and a vector now, which is also partitioned after two entries. And so these will be partitioned conformably, meaning that we can actually multiply the individual elements. So when I draw this partition and give this new name, I have a much simpler problem to do, or at least it looks like I do, right? Because whereas here this is a 4x4 matrix times a 4x1 vector, here it's a 2x2 matrix times a 2x1 vector. And I can actually multiply these things out, the notation out, so I have B times U plus C times W. That's just row times column. But that's not going to be a single number, right? Because B is 2x2, U is 2x1. So B times U would be 2x1. C times W would be 2x1. So there are two entries on top and two entries on the bottom. And be careful, this is not a fraction notation. This is the partition notation. So there's two entries up here and two entries down here. So if we actually work out all that multiplication and addition, we're not really saving any time in this computation. What we're going to do is save time in the notation. And oftentimes we'll be able to represent unique concepts by ordering the rows and columns into special blocks. Okay, so if you actually work this out, this matrix B times this top half of the vector, and then this second half of these rows multiplied by the bottom half of the vector, everything's working out to be exactly the same. You can actually do this computation if it's going to make you feel more comfortable, if you can't see it right away. I have an exercise coming up that I suggest that you do so that you can convince yourself that all of this is okay. So in one of the previous worksheets, I believe it was worksheet 4, but I'm not sure, we worked through several views of matrix multiplication. Talked about it as a collection of inner products, as a sum of outer products, and that turns out to have major implications. None of the exercises I have you do are just for fun. They're all leading us to very specific things in the future of this course. What we're going to have to do is basically get through an undergraduate and a graduate course in linear algebra, and we're doing that in about, 15 lectures or fewer. So everything is very targeted. There's nothing that you're learning that you're not going to need to use later on. And so these views of matrix multiplication that we took are exactly what we're about to see in this partitioned form. And this will help us when we start to try to understand the singular value decomposition. Even when we start talking about covariance matrices, everything starts to click a little bit more. So let's start with our original formulation of matrix multiplication. And this is where we just multiplied row times column, row times column. Oops. So let's talk about a matrix X. And so here I'm writing X as a collection of column vectors, and there's P of them. I'm using the variable P because oftentimes we talk about having P variables when we do regression. And then X transpose. So X transpose will have rows that come from the column of X, right? And those column vectors are going to be transposed. So it's got X1 transpose through XP transpose. Now, what can we say about the matrix product X transpose X? So this collection of row vectors times this collection of column vectors. X transpose X. First of all, we might say, or ask ourselves, is this partitioning conformable for multiplication? Well, what do we mean by that? We're always going to want to multiply row times column. So even when we have blocks, the whole idea is to make these blocks, simplify our notation, and then almost pretend like these blocks are individual numbers. So we're going to multiply row times column, row times column, row times column. But they're not individual numbers, so we have to make sure that what we're doing actually makes sense. Can I actually multiply X1 transpose times X1? So we can do a check on that real quick. And we won't need to check this when we're actually doing this in practice, because I'm never going to put something up that's not conformable. So you'll most often just see things written this way, and I want you to understand what's going on in the background. So each row vector here, each row of X transpose is 1 by n, because you remember that, I guess I didn't say that. Well, X is an n by p matrix, so n observations, p variables. So each one of these rows is 1 by n. Each one of these columns is n by 1. So yes, there's no problem. We can multiply each of these, and the result of each calculation will be a 1 by 1 matrix, or a scalar. Right? And this looks like the form of an outer product. So we know that when we multiply this column times a row, what we're going to get is a larger matrix. So first row times first column, X1 transpose X1. Row times next column, X1 transpose X2. And so forth, carving out this large P by P matrix. This form of a matrix is something that we're going to see a lot of. It turns out that the covariance matrix can be written as a form sort of like this. The correlation matrix is not too different from this. And we also already saw this matrix, this very matrix, when we talked about least squares in the normal equations. One thing that you might want to realize about this matrix is that these diagonal elements, these are going to contain the sum of squares for each column, for each variable, right? Because when I take a column vector and I take the inner product of that with itself, what I do is I end up taking the sum of squared elements in that vector. It's another very important point. Now, another way that we're going to end up using this is to represent that opposite formulation, where the matrix on the right is partitioned into columns, and the matrix on the left is partitioned into rows. So here I have some matrix U, that's M by R, and a matrix V transpose, which is R by N. And this is actually something that we're going to come across a lot. This comes out in factor analysis, the singular value decomposition, principal components analysis. Pretty much any dimension reduction technique can be represented as a matrix factorization, and it's going to look something like this. And now when you see a transpose on a matrix, oftentimes you will, what that means is that we're really worried about the rows of that matrix, or the rows of that matrix are what's interesting to us. And so oftentimes when there's a transpose on a matrix, you'll even see that matrix written this way as a collection of rows, because those row vectors are what's interesting. Otherwise, there would be no need to define a matrix with a transpose. Okay, so here I have this matrix U, and it's partitioned into R columns. And I have a matrix V, which is partitioned into R rows. So this partitioning is nice because what I'm going to do is just multiply this row times this column, as if I was dealing with individual numbers, even though I'm not. So U1 times V1 transpose plus U2 times V2 transpose, and so forth, up to this final element, UR times VR transpose. So this is kind of like an inner product of partition matrices, right? Just one row times one column, and then what I end up with is a sum. Now let's back up a minute. Let's just talk about whether or not this partitioning is conformable for multiplication. What are all these terms right here? Because I know if I multiply a U that's M by R and a V that's R by N, that result should be an M by N matrix. So I need to make sure that this result that I'm getting is an M by N matrix. So again, we want to multiply row by column, and if we do that, in this case, we're going to be multiplying these UI's times the VI transpose for each I, and then we're going to add up the result like we just saw. Do these calculations make sense? Well, UI is going to be a column of U, so it's going to have M rows in one column, so it's M by 1. These VI's will be a row of the V transpose will be a row of V transpose, and so it's going to have N elements, N columns, and one row. So you can see, yes, absolutely, these things are conformable for multiplication, and each of these terms is actually going to be an M by N matrix. So backing up here, I am taking the sum of several M by N matrices to get this product result. So oftentimes, the way that we're going to use this is to write a matrix as a sum of all these different matrices, and then we're going to try to find out what's important in that matrix. Okay, but we're not there yet. Right now, we're just trying to get a handle on the notation so that everything doesn't look alien when we get there. So this is a good place to try to check your understanding. What I want you to do is to compute this matrix product using block multiplication. So let these lines be your guide. And so this is technically, we're looking at this like a 2 by 2 matrix. Same here, 2 by 2. And I want you to multiply row times column. for each of those blocks. And then here's the solution. So if I just do this multiplication out, this is the answer I would expect to receive. And then I can break that computation into the 4 blocks. So the first block, I have the kind of the 1, 1 element times the 1, 1 element plus the 1, 2 element times the 2, 1 element. And that gets me here. I don't think I can read out all of those element-wise, but hopefully you're able to work that out. So that's all we have for Chapter 2. Enjoy the rest of your day.